Okay, so I think I'll get started. So for the Dartmouth folks, I wanted to make sure that you understand that next week is UMass spring break. We don't have classes. I will be away. So the classes will resume the Tuesday following that. Then the other thing I want to highlight is I finally tracked down Feynman's early paper on the quantum theory of gravity, Acta Physica Polonica, which no longer seems to be easily available. So I put it on the webpage. I do recommend it as a reading. It's really entertaining reading. You get to, it's actually a recording, so it's in Feynman's own voice. And it has a couple things. It has, in there, it has not only the Fidea Popov Gauss, but it also has Feynman's tree theorem, which is the connection between trees and loops, which is a big deal these days in calculating processes. So if we get to that at the end of the semester, it'll be nice. But if not, you can read the start there. Okay. Where we ended was we had actually completed the quantization. So we had a background field, which I've now dropped the bar. Now this is G is just the metric in general. And we've written it as a path integral over all the fields involved. So the quantum fluctuation is now just like any old matter field. It has covariant derivatives and you just integrate it. There's the Gauss, which are a bit funny. They are fermions, yet they have bosonic propagators. Any field you want. You can add sources for the fields. Actually, this should be G mu nu. Sorry, that last one should be G mu nu, not H mu nu. H mu nu is integrated over. You can add sources for the fields if you want, but you don't add sources for the Gauss field. So, any question on that formulation there by itself? Anything you want to ask?
So the Gauss is purely virtual particles,
right? So
so has there been some experimental way of their actual effects?
Well, so no, so really they're a calculational trick. So the question was, have we seen Gauss? And the answer is, in some ways, you've seen the effects of Gauss in QCD when you look at the running coupling constants, because they're an important ingredient into the running coupling constants. So in Yang-Mills, there's the Gauss also. They propagate in closed loops. So when you do vacuum polarization diagrams in Yang-Mills, you have to have them in there. They contribute to the beta function for QCD. So if you're saying, where do they appear in real calculable physics, it's right there. Okay. But they don't live as external states, so you don't see them in that sense. Okay. And really what so remember again, they're compensating for the unphysical degrees of freedom that you've got when you do covariant quantization of the gluons or gravitons. Gluons have only two polarizations, the gravitons have only two polarizations, yet when you do the propagators for them in a covariant gauge, like for Yang-Mills, you have G mu nu, there's 4 terms there. The Gauss remove the unphysical ones.
QED, covariant gauge, you have 4.
Right.
So what about, there should only be 2?
So
there's no Gauss in.
Yeah, and so that's right. So in QED, the same thing happens. There's no Gauss because they don't need it. Okay, and that of course explains why QED was able to be quantized before we knew about Gauss and the like. It's in some sense good luck that we didn't need it there before we figured them out. or Feynman figured them out. Okay, and you know, in some sense, remember when I was telling you the ghost stories about it, about how he figured it out. He was basically he was doing calculations by putting physical intermediate states there, and realized that he was getting the wrong answer if he just put normal propagators there. And so he put these guys in to remove the unphysical stuff. It's very insightful. You read the paper. It's actually interesting because what he does, the Feynman tree theorem is a way of calculating closed loops where you only do tree diagrams where you put the intermediate particles. So tree diagrams are those without loops, and you put the particles on their mass shell, and you can reconstruct from that, from these multiplying together tree amplitudes, you can reconstruct the properties of closed loops by using unitarity and analyticity. So that's okay. Any other questions, Dartmouth guys? Okay. So let's move on to the one loop divergences. Okay, the easiest thing to calculate is the divergences because they're local. In principle, you could just do this path integral and you'd take any matrix elements that you wanted. You just, then expand, find a matrix element, and you've got the one loop corrected matrix elements. Some of the finite stuff is tough to pull out. We'll try pulling some of it later. But the divergences are easy. That's the easy stuff. So let me just recall what we did for scalars. Okay, we did it first in this following way. We did it in flat space. We didn't actually do all the steps, but it's just a usual Feynman diagram. And we found that that was some constant times kappa squared over 16 pi squared, 1 over epsilon minus stuff plus log q squared. And then there was a bunch, q is the momentum here, of tensors, because this has indices mu, nu, alpha, beta, q mu, q nu, q alpha, q beta, plus all sorts of other stuff. Okay, so there's some big tensor. Some big tensor there. The second way we did it is we came back and we did a heat kernel where the mathematicians have done all the work for us, and we found that this was equivalent to delta S divergent was integral d for x square root of minus g. Here I know the constant. It was 1 over 180, 1 over 16 pi squared, 1 over epsilon, dot, dot, dot. And the formula was r mu nu alpha beta, r mu nu alpha beta, minus r mu nu, plus it was 5 halves 6c minus 1. C is this conformal parameter. That was squared times r squared. Okay, and these match term by term. Basically, you take r mu nu alpha beta, goes sort of like d mu d nu h alpha beta plus lots of other terms. And if you take these guys and express them then in terms of derivatives on H, and you take a matrix element, you get the same tensor up there. Okay, and it's amazing that we've also matched, even though I've not done the calculation, things like that and things like that. All the divergences that happen at higher orders come out at the same thing. There is one caveat. There's really only two terms. Oh, the curvature squared. Okay, I did write out that's the correct A2 coefficient. The A2 coefficient has many uses, so I gave you the full coefficient. But it's not but we're going to get rid of one of the terms. Okay, and so that's what I have to explain now. The getting rid of one of the terms is the Gauss Bonnet in identity. Gauss B. So Gauss Bonnet is this term. And this is in 4D, in 4 dimensions. If I take G, this is the Gauss Bonnet invariant. It's R squared minus 4 R mu nu plus R mu nu alpha beta, R mu nu alpha beta. That's the total derivative, total covariant derivative of some current. So it's the total derivative. Okay, the current, I have not worked this out. I am copying this from somewhere, but let's put it, it's mu alpha beta gamma epsilon rho sigma eta nu. I was just curious to see what it looks like myself. Sigma nu beta gamma plus 1/3 gamma gamma. Let's see. Alpha beta down here. Sigma up here. Nu gamma. No, that was lambda. Lambda. There we go. That's what it should be. This guy down there should be a lambda, I think. Yeah, I'm missing something, aren't I? Yeah, I'm missing something. What am I missing? Yeah. All right. Let me put a question mark here. As I told you, I copied it. I didn't copy it very well. Oh, no. Here's what it is. I see it now. There's a gamma rho eta alpha. There we go. Now we got enough indices. Okay. But the interesting thing is that, again, this is copied, but I know up to the normalization, I know that the answer is right. D4x squared minus G times this Gauss Bonnet invariant is the Euler characteristic of the manifold. Okay, so it's a geometric quantity. The Euler characteristic is related to the number of handles on a manifold. So, whether it's a sphere or a torus. Okay, so it's a beautiful mathematical quantity. So You see this in the geometry more. For us, it has the following meaning. Okay. Let's see if I can. So it's a total derivative. So that we then end up with integral d4x square root of minus g. G is a surface integral. Okay, we've run across those before. That means it does not influence the equations of motion. Okay, any surface term doesn't influence any local dynamics. It does not influence any matrix element. Okay, this is basically a consequence of momentum conservation. The momentum flowing in is the same as the momentum flowing out. And then the fourth thing is that the integral d4x square root of minus g r mu nu alpha beta r mu nu alpha beta can be written in terms of the others. R mu nu, and r squared. And that actually, there is some physics in that. We'll see that there are cases where the Riemann curvature, the one with the four indices, doesn't vanish, but r mu nu does. Okay. So let's go back to the scalar field. The divergent pieces really are then equals, well, let's see, up here we had 1 over 180, 16 pi squared. So let's just rewrite that d4x square root of minus g, 1 over 180, 1 over 16 pi squared. That's the piece that's carried forward. You then take the remaining pieces and write it as 3 r mu nu minus a third r squared. And then there's this other last piece here, which is 5 halves 6c minus 1 r squared. And clearly the r squareds can be combined up, but it just makes it algebraically messy to write it out that way. Okay. This actually has questions to this perturbative matching here. It means that if I took, let's imagine I started with my tensor here to start with, all the ones I've done the perturbative calculation for. I couldn't reproduce these three terms because they're redundant. However, I can reproduce two of them, the two terms. So you can do perturbative matching if I take this 1 over epsilon, q mu, q nu, q alpha, q beta, this can go into any form you find there can go into 1 over epsilon, some a r mu nu, r mu nu plus b r squared. That's a unique solution. The two structures that you have there are algebraically distinct, and so any tensor that you have can be broken down into the two of them. Okay? So, gravity, one loop divergences in gravity.
John,
Yes?
can you actually say one more word about what exactly you did in the perturbative matching?
Okay. So what you do when you have this is you have this big tensor that has terms that I wrote out one term, but there'd be another one, G mu nu,
Right.
Q alpha, Q beta. And what you do on this side here is you write R in terms of d mu, d nu H plus, there's a bunch of terms here, box H mu nu. And then you take matrix elements. So this guy turns into Q squared times G mu nu.
All right.
Okay. And then you write out the tensors that appear, and you look at the tensors that were in your perturbative calculation,
Yeah.
and you'll find a one-to-one correspondence.
All right. Thank you.
Okay.
Yeah.
Okay. So you can, in the case of gravity, you can do the same thing. You can either do the perturbative calculation, which is this diagram with gravitons plus the diagram where you have these ghosts. And I've done this analytically in this one on a computer because the multiplying together those tensors is a pain. Or the second way you can do it is the heat kernel, which is basically what Tufts and Veltman did. If you look at their paper, what they're doing is calculating the heat kernel for this. And the answer has the following. It's so this A2 coefficient for gravity. If you carry all the terms along, which is 215 over 180 r squared minus 361 over 90 r mu nu plus 53 over 45 r mu nu alpha beta r mu nu alpha beta. And if you reduce it, it looks a little better. It looks like 1 over 120 r squared plus 7 over 20 r mu nu r mu nu. Okay. So this is the form given by Tufts and Veltman. This one I found in some other math literature. I hope they reduce it down. I've checked it once. I hope I did my algebra right. But the Tufts and Veltman one is the known result. And so the divergence is then S divergent is 1 over 16 pi squared 1 over epsilon plus blah, 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 times this 1 over 120 r squared plus 7 over 20 r mu nu, r mu nu. Okay, that's in some ways the major result of Tufton. Okay. Now, sometimes you'll see the following said, and it's certainly true. Here we've calculated the divergence, but you'll see it said that pure gravity is one loop finite. So both these statements are true. Okay, you do the one loop integral, you get a divergence, yet pure gravity is one loop finite. And the argument is the following. So if you do pure gravity, the equations of motion are r mu nu minus 1/2 g mu nu r equals 0, which then implies that r mu nu itself is equal to 0. Pure gravity, note that r mu nu alpha beta is in general not equal to 0. So the Riemann tensor is not 0, but the Ricci is. And when you did background field method, you used the equations of motion to eliminate the first order term. That's equivalent to using the equations of motion, that it's okay to use equations of motion in S divergent. Okay. Okay, so in the absence of matter, there are no divergences. So no divergences in the absence of matter. Okay, so let's imagine doing graviton-graviton scattering, which is blah, blah, blah. I'm going to show you this later on. There's a whole bunch of diagrams that go like this and like this. That's tree level. And then you start doing things like this, which is a divergent diagram. And let's do that. The divergent diagram, plus, 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 plus. You'll have no UV divergences, no high energy divergences. Okay, this has been calculated. I'll show you the answer, and it's true. Okay, so this was a little piece of excitement. It's not that you didn't have to do the calculation. Once you know the Gauss Bonnet, you know there's only two terms, two counter terms. You know it's going to be local because divergences are local, and then you know that you can use the equations of motion and you're done. So you didn't have to do the calculation to show this. But nevertheless, that's what it is. However, it's not that, in the end, it's not that useful. Except in special cases where you forget about matter, just because matter does exist. And in the absence of matter, these divergences have physical meaning. They're there. Okay, so matter exists. So there are one-loop divergences in general. And in fact, if you put matter in, you might try looking around to see, is there some combination of matter where all the one-loop divergences cancel out? And there isn't. That was in fact the topic that was discussed in that quote that I gave you from the end of the Tuff-Veltman paper. They said they've been trying, they can't be guaranteed it's not going to work, but a certain exhaustion sets in. Okay, and the answer is it doesn't. And there's also there's a two-loop divergence anyhow. In pure gravity. And the two-loop divergence looks like this. It's so it's an effect. The divergent piece looks like here. It's 209 kappa squared over 2880 pi squared squared 1 over epsilon plus blah blah blah. R alpha beta gamma delta R gamma delta eta sigma R eta sigma alpha beta. And that's one I don't guarantee the sign on because there's sign conventions involved. This was calculated, I always call this a heroic calculation by Giroff and Sagnoti. One loop is hard enough, two loops is tougher. So you can't get out the fact that pure gravity is finite because here's a divergence that exists. So it's not worth even trying. But for us, I do want to note the following. We started with the curvature. So no loops, we had the curvature. At one loop, we had curvature squared. At two loops, you see the result was curvature cubed. Okay. Curvatures have two derivatives. Curvature squareds have four derivatives. Curvature cubes have six derivatives, of course, then. And we're starting to see one of the essential features of the quantum theory, which is that the number of loops gives you higher and higher numbers of derivatives and higher powers of the curvature. Okay? That's good and it's bad. The bad feature is that you're getting something new every time you do another loop. This is the hallmark of a so-called non-renormalizable theory. There's basically, you're not renormalizing your lowest order Lagrangian. you're generating new Lagrangians as you do loops. So that's the bad feature. But we'll turn this into a good feature, because then to do any particular calculation at a given level of accuracy, you have to only do a small number of loops. Okay. So let me just close with a little bit of summary of philosophy and the like. So this section here was on quantization. And historically, there are two paths. There was canonical quantization. Okay. So canonical quantization in general refers to forming canonical momentum from the variation with respect to the fields, opposing canonical commutation rules, phi, pi at equal times is IH bar, delta functions, etc. Canonical quantization is not good for theories that have self-interactions and are gauge theories. Okay, so in general, for example, easy flaw you can see in QED is that the canonical momentum, which would be the variation of the Lagrangian with respect to the time derivative of A0, doesn't exist because F mu nu is antisymmetric. There are no time derivatives of A0. So this only gets worse in other theories. There's no practical quantization for Yang-Mills, at least that I know of. It's not how you do Yang-Mills. In gravity, people set out there's the ADM formalism. ADM stands for Arnowit, Deser, and Misner. And it's in some ways a beautiful formalism, but not that practical. For example, you can't calculate the divergences that we just did using it. You can't calculate scattering amplitudes with it. You can formulate true statements, but not. And it's easy to see that gravity is the last theory that you'd be wanting to do this with. You don't have equal time commutators because you don't even know what your times are. You don't like separating space from time because you're all tied together. So while it's obviously the first thing to do, it's not necessarily the best thing. The path integral way is the one that worked. And here the pathway goes from Feynman. So if you read that paper, you'll see that he presents the original discussion in terms of Feynman diagrams, but then when push comes to shove, in the comment section, and DeWitt is there pushing him to explain better what he does. He pulls out path integral, so it's clear how he was thinking about it. Feynman, DeWitt. There was some, in the 70s, there was a lot of perturbation theory done. There are a lot of British guys. So I don't know how to better say it. Mike Duff, Christensen, Capper. There's a lot of good work that's buried in the 70s literature on perturbation theory. Then came along Tufte and Veltman, and that's in some sense the definitive treatment. But all of these had the same features. Their focus was on the divergences. Okay, and I'm going to try to convince you soon that that's not the place to look, that we have better things to do. Okay, so all of this led to, in some sense, a bad reputation for quantum gravity. Okay, so some of it was this old style quantization. Some of it was just fuzzy thinking. Okay, it's easy to get yourself very scared if you start thinking about delta x, delta p is h bar, and you're working in curved space time, and what's my delta x and what's p's, and it's very easy to get space time fluctuating, and how do I define delta x? These ills, in some sense, were cured by the path integral. The path integral treatment is a very precise and useful way to deal with it. However, even after the path integral treatment, there's some bad stuff. There's the fact that the theory is non-renormalizable. There are these infinities. These, in some ways, are cured through the passage of time. It's understandable that they were bothered by it. I'll be a bit cute and say it's cured by the effective field theory. But the basic point is that we nowadays have a different relationship with infinities. I don't know what your relationship with infinities is, but the present relationship is much more tolerant, much more diverse. You can take all sorts of infinities, and I'll explain why when we do the effective field theory. But we can live with and deal with non-renormalizable theories and make experimental predictions in non-renormalizable theories. We've come to understand some field theory better. However, then there are still some things that are not yet cured. We'll see that even the effective field theory doesn't tell us anything about the final theory of quantum gravity. And there's all sorts of puzzles that are going on now, such as information loss. non-perturbative treatments. These are open still. So the bad reputation has some things that you'll read about in history that are just not meaningful anymore. Some that have some meaning, and some that are still the focus of the field. Okay. Yeah. Well, yes, we could. Yeah. So when you think of the theory in terms of the fields, so it's really not, the space-time is really the coordinates on a manifold, if you want. It's the metric that's fluctuating, and we're actually able to deal with the fluctuating metric by doing that path integral. Okay, and then you can ask precise questions of the residual after you've done the path integral. Okay, so my next topic is going to be effective field theory, and effective field theory helps clarify this thinking. So there's a lot of thinking historically that's, some of it's good, some of it's bad. The effective field theory's value is it helps clarify the thinking. Okay, ready for effective field theory? Any questions about what we just did?
I have a question that dates back a little further.
Okay.
When we talked about the one loop divergences,
yes,
you made an argument how we could use the background equation of motion to say that r mu nu is equal to 0, but I don't understand how the background equation of motion is still valid at one loop.
Yes, well, okay, in some sense, this is also, it's a perturbative statement. We're doing perturbation theory, and the background that we're perturbing about was chosen to satisfy the linear equations of motion.
Yeah.
Okay, so this is a statement about the background.
Mm-hmm.
And it's actually only true at one loop, or only true
at tree level.
It's true at tree level.
Yeah.
But that's the background we're perturbing around. We've calculated the quantum fluctuations there, and if we were to take the next step and try for the two-loop result, we would have to use the equations of motion that are valid at one loop.
Okay.
So we'd go back, redo the equations of motion at one loop, and then calculate yet another loop. Okay, so it's very much a perturbative statement.
Okay.
Okay, so it's actually an interesting question for Mr. Giroff and Signoti on how they did it, which I can't recall. They had to do the two-loop equations, so they had to do something about that. Okay, does that answer well enough for you?
Yes, thank you.
Good. And did you here in the room hear enough of the question that? Okay, good. All right. So here we go. EFT, effective field theory. Okay. If you've heard me give my effective field theory talks, you know I always start on the following question. And that question is, why do quantum calculations work? Okay. Now, well, we of course know they do, but in some ways it's a surprise. When you're even doing quantum mechanics, you might look at some state where you start in some initial state, you have some interaction, you've got an intermediate state back to maybe some final state, either the initial or final, E minus E intermediate, summing over all intermediate states. The trick is that this says all intermediate states. That means that if you're summing over states, it includes arbitrarily high energies, and physics is an experimental science, and we have not probed to arbitrarily high energies. So how do we know that there isn't some intermediate state, some particle that lives at 100 TeV that we haven't yet discovered, that enters this intermediate state sum? Okay, or if you're doing loops, you have to do, here's some process, there's some loop diagram, or there's another loop diagram where there's new particles there that are not yet discovered. Okay. And so when I ask this in quantum mechanics class, types of things people say are, well, there's an energy denominator. That's actually not the right answer, because in fact, this sum is really the integral d3p when you do continuum states. So in fact, it accentuates high momentum states. And so all the standard answers of these high energy states don't contribute actually are not correct. All of physics is sensitive to high energies. And we'll see how that can be. And so the answer actually isn't that. The answer has to do with the uncertainty principle. And locality. Okay. The basic point is that from the uncertainty principle, delta x, delta p is h bar, delta e, delta t, that very high energy stuff corresponds to very short distances and very short times. Delta x, delta t, small, which implies it's local. And if it's local, it looks like some term in your Lagrangian. Because the Lagrangian contains all the local pieces that you're interested in. And these local pieces come with coefficients. Parameters. Like the electric charge, the mass, any coupling constant. And you end up having to go out and measure these. And so the unknown stuff goes into renormalization constants. Okay, it's not so much the divergent, it's just that they're unknown. And the statement that all physics is sensitive to high energies just comes because divergences is one of the parts of high energy stuff that we don't know about. And so it's an example of high energy physics that we don't know about, but we're sensitive to. Okay. What I'd like to do here is just look at an example of how this works. So the example is again the vacuum polarization. So we've calculated this. Okay, and let's imagine that I put a very, very heavy particle there. Okay, when you do the vacuum polarization, you know that that goes into the renormalization of the electric charge. So you basically, you take this guy plus that guy and write this as, well, it's 1 over q squared, the bare charge squared over 1 minus pi of q squared. And pi of q squared I've copied here. This is the result for a fermion. Okay, and the case that we're studying is when m is much bigger than q. So there's the form. And you know that if I do ms bar renormalization, that I'm supposed to absorb the 1 over epsilon and the 4 pi's and the gamma into the renormalized electric charge. So I would, for example, in this case, take E ms bar squared is E0 squared 1 minus E squared over 12 pi squared 1 over epsilon minus gamma log 4 pi. Okay. This actually looks a disaster if you look at it. Because I have this log of the heavy mass left over. So that heavy mass would then say that I've got 1 over q squared EMS bar squared 1 minus E squared over 12 pi squared. I have a log m heavy squared over mu squared. And it would look like scattering depends on this. It doesn't. Okay, and the basic reason is that the MS bar is not what you measure. You actually measure the zero momentum. When you measure, it disappears. Okay, so when you're measuring, you actually measure near q squared equals to 0. Of 1 over q squared E0 squared over 1 minus pi of q squared, which goes then into 1 over q squared E0 squared 1 minus pi of 0. And so the measured value E physical includes pi of 0, actually absorbs the log mh squared. And E physical squared over 4 pi is our 1 over 137. So that's the number that we've measured. So in fact, this was sensitive to high energy physics. It was in principle sensitive to log of the heavy mass, but the log disappears because it's in the measured quantity. So that's good. Quantum mechanics actually now can work. You can make a prediction. You don't need to know the log of the heavy mass. The residual effect is suppressed. Sorry. Okay. The residual effect, it comes from the q squared over m squared. So we end up with the effect here, 1 over q squared. What I started off writing is 1 minus pi of q squared. I absorbed the pi of 0 into q squared equals to 0. And this then looks like E physical squared over q squared. And then the next order piece there is plus q squared over 5m squared, 1 over it's e squared over 12 pi squared. 1 over, I'll just write it as 1 over q squared times q squared. I've Taylor expanded at this stage. So these guys cancel each other. The first term gives you your 1 over r potential. The second term, the Fourier transform, gives you a delta function. When you Fourier transform, gives you a delta function of the distance. This guy goes into Lamb shift, etc. So we've seen this story in field theory. But the feature here is that it's suppressed, and you don't then end up having any residual effect. This actually goes by the name of, this effect goes by the name of the Appelquist Carazzone theorem. I always forget how many Z's, N's, and R's there are in Carosone. So don't trust my spelling. But the Appelquist Carazzone theorem says that the effects of a heavy mass particle appear either as a renormalization of a coupling constant or a power suppressed correction. So the stuff that goes into the coupling constant gets disappears into the measured value, and then the power suppressed is small. So that's why quantum calculations can work. So we've seen these. There's two caveats, two things I want to say here about that. One thing to say is that in effective field theory, this is not just a heavy mass particle. It's so what Appelquist Carazzone say is heavy mass. It means all high energy stuff. So even if you have light particles around, and in the loops they have very high energy behavior, in the loops where the momentum is very high, the heavy high momentum components of loops obeys this also. It either goes into renormalization of a coupling constant or is power suppressed. So sometimes we will separate out the high and low momentum pieces of a single particle. Okay, the other caveat or the other thing to say is there actually are violations of this. It's not true if the limit violates the symmetry. The symmetry of the theory. And there's a very famous example, which is the top quark lives in a doublet in the standard model. If you were to take the top quark mass to infinity, Appelquist Carazzone theorem doesn't apply because the theory then would have only half of a doublet there. Such a theory would need more terms than are required by symmetry to renormalize it. And so there'd be new effects. And this explains why in the standard model, there are mt squared effects that get arbitrarily large as you get to top masses. But if you took both mt and mb to infinity, there are no large effects. So you take them, you put them in a doublet, make the masses equal and take the masses to infinity. You don't get diverging effects like you do if you just take the top quark mass. Okay. All right, so maybe I'll stop there. Next time we're going to go through the principles of organizing an effective field theory and start an extended example. Okay, good. Let me stop there.
Thank you.
Thanks.
There. Yep. Bye-bye.